All right, it's just about 10 a.m. Can you guys give me a thumbs up if you can hear me okay? I think I see a yes. So let's
Oh, sorry, I was muted. Oh, you actually froze for 1 second. Can you?
oh, yep. Can you hear me okay now?
Yeah.
Perfect. Okay, so let's get going. So as you know, we are just sort of continuing through our chapter 2 things that we're learning about the derivative and the derivative function. As a reminder, there is another review session on graphing functions and their derivatives on Thursday. I sent you an email about that, and the link is also posted on Moodle. So that's sort of what we were working on last time, and we'll continue to work on throughout this week. And so if you think you could use more practice graphing the derivative and understanding sort of how those things relate, then you can check out that on Thursday. And I will post the video from that after Thursday's meeting onto Moodle under the Getting Started, which is where the other review videos are posted. So additionally, I just want to remind you that our chapter 2 quiz is coming up next week on Tuesday. So it's the same as the chapter 1 structure. There's 10 multiple choice questions. You'll have the entire day to figure out when you'd like to take it. It'll open right at midnight, and then I'll close at 11:59. And again, the best way to practice and study is to go through your old mini quizzes, make sure your notes are organized, and go through homework. So make sure that you stop by Drop In Help if you need help with any of those pieces as we sort of move towards that chapter 2 quiz next week. So today we're going to be going through 2.3, which is called Interpretations of the Derivative, which has 2 pieces. It has units that we'll talk about first, and then what's called the tangent line approximation, which is a method that we're going to learn that helps us predict other values. And then we will start 2.4, second derivative, but not get too far into it. And then we'll pick that up on Thursday. So that's sort of our plan here. I'm going to switch over to the dot cam here. Give me 1 second. Okay. So like I said, the first part of the class, we're really going to be focusing on units. It's something that we haven't done a ton of. We talked about units a little bit in chapter 1, but now we're going to learn a little bit more about how we talk about the units of the derivative. And then from here on out, we'll be able to apply units whenever we have units that are important to the problem that we're talking about. So thinking about units, I just want to circle back to notation. So I can't remember how in depth we talked about this, but in the late 1600s, there were 2 people working on differential calculus, which is the calculus we're studying, at the same time. So, you know, Newton was working on it and Gottfried Leibniz was working on it. And there was controversy about who actually discovered calculus. And the reality is it's probably neither of them, because there's definitely evidence of other people having similar ideas in other countries. But the reality is that both the notations have carried forward. So Newton's notation and Leibniz's notation are still both used today in common calculus courses. So we have 2 ways to describe the same thing. And so the common ways we talk about the derivative, we have the f prime, which is Newton's notation, and we have dy dx, which is Leibniz's notation. And for the purpose of units, Leibniz's notation helps us better understand the units of the derivative. So when we talk about dy dx, which is the Leibniz notation, it's talking about the derivative of the dependent variable with respect to the independent variable. So you might see this as like dy dt, if t is the independent variable. Or you could have something like dm dt. What that tells me is m was the dependent variable and t was the independent variable. So either way, these all are talking about a first derivative. And so one of the ways we sort of think about this ratio, right? We can link that directly back to our average rate of change. But we're thinking about the difference in the y values and how those change as we change the x values, and our units match up the same way. Okay, so what does that mean? That means when we take the derivative of a function, the units of the derivative are going to be the units of the dependent variable over the units of the independent variable. right? So that sort of matches up with our map of the Leibniz notation. And so when we think about this, what are we going to need to do? We're going to need to identify what the independent variable are and what their units are, and then we will be able to attach that to the derivative. Okay, so let's look at a practice problem here. So suppose that the position of a falling stone is given by S of t in meters, and time t is given in seconds. Okay, so we're measuring where the stone is in space and it's falling. Its position is the dependent variable here, and the time at which we're measuring it is our independent variable. So if we're talking about f prime of 4 equals -7, what does that mean, right? So a lot of the stuff we'll do today is what does it mean? So we need to figure out what these numbers mean in this context, okay? So the first thing is that when you have f prime of 4, this 4 is still related to your independent variable, right? So remember, the independent value is what we plug into the independent variable. And so this 4 would get plugged in for time. So it doesn't matter if it's the original or the first derivative, the number that you are plugging into the function is from the independent variable. So this 4 here is going to get paired with our independent variable, which is time in seconds, right? So the 4 is talking about 4 seconds. Now, the -7 is the derivative value. So the -7 is where we have to apply this idea that our units are going to be the dependent units over the independent units. So my dependent units here have to do with the dependent variable, which is S of t. And so those units were in meters. So here, I'm going to put meters on the top for my dependent units. And down here, I'm going to put seconds for my independent units over here. So when I'm talking about the derivative, I'm talking about -7 meters per second. So let's put this in the context of this problem, right? So we're talking about a stone that is falling. So what this means is that after 4 seconds, so at time equals 4, the stone is falling at a rate of -7 meters per second, right? So that is the speed or the velocity at which it is falling, and that is the derivative. So notice that the derivative has units over units, so something per something. That's sort of a good way to try to remember that you need to think about what those are. So again, the number that's inside is your independent value. And then the number on the outside of the derivative function is the value of the derivative, which is when we have to do dependent over independent units. Okay, so we're going to skip the statement for a few minutes until we get to tangent line approximations, because I want you to start practicing some sort of unit applications here. Okay, so we're going to look at example 1. I can get the paper to stop moving, which is similar to the one we just looked at. So if S of t is the position of a moving object in feet, okay, so now we're in feet, and time is measured in seconds, find the units of the derivative of S of t, which we also call velocity, right? So the derivative of position is called velocity. So you're going to do the same sort of thing we did in the previous problem, where you need to think about the dependent units over the independent units. If you're comfortable using notation, it would be great to set up the notation for this. Usually Newtonian notation is fine. And then part B says if the velocity, now we're going to call the velocity v of t, as per the instructions here, of an object has the units found in part A. So what the units you find in part A are the units of velocity. Then what are the units of acceleration? A of t, which is the derivative of velocity. So you need to do part A first to get those units, to then try to figure out the units of part B. Okay, so I'm going to give you 2 minutes to try to think this through. If you only want to do units, that's fine. But if you're comfortable also writing out some of the notation for derivatives, I think that will be helpful for you to connect everything. So take about 2 minutes and then we'll go through it together. So take about 30 more seconds to finish up whatever part you're working on. All right, so let's go through this. So for part A, we have the derivative of position, which we're calling velocity. And so the way we usually notate velocity is v of t. But in order to find the units of velocity, we need to go back to this position function and figure out what are the dependent and what are the independent units we're talking about here. So the position was given in feet. So that's our dependent units. And then we're told that time, which we're plugging in, which is in seconds, is going to be our independent units. So if we are trying to get the units of the derivative, we're going to do the dependent units over the independent units. So here, that's feet per second. So you will often see this abbreviated like this, feet per second, right? So those mean the same thing, but the idea here is that we have the dependent units over the independent units. That's what's going to be the units of the derivative of position. Okay, so that's part A. Now remember that the derivative of position is called velocity, right? So the units of velocity are in feet per second. So for part B, it says if the velocity, v of t, right, has the units found in part A. So the units of velocity are in feet per second. So I'm just going to underline this and I'm going to write feet per second just right near it. Then what are the units of acceleration, which is the derivative of velocity, right? So here we're looking for v prime of t, and we're saying that's called acceleration. What are the units of that going to be? So what do we need to know here? We need to know the dependent units of velocity and the independent units of velocity. So the dependent units of velocity is the feet per second, right? So velocity is given in feet per second. So that's the dependent units. So up here, we're going to have feet per second. And we need to divide that by the independent units of velocity. Well, the independent units of velocity are the units that you would plug into velocity, right? Which is the same as the units you'd plug into position, which is time. So the independent units here are also in seconds. So we have feet per second, right? So we can simplify this into feet per second squared, because there's two of them. If you divide seconds by seconds, they combine and become seconds squared. So the units of acceleration are feet per second squared. Now remember, this is the derivative of velocity, which is giving us this acceleration. And so I want to sort of hint at something we're going to get to later today, but the derivative of velocity is the same as taking another derivative of position. So the second derivative of position, and we're going to talk about second derivatives later, is the same as the first derivative of velocity, which is acceleration. Okay, so this is just sort of like a preview of where second derivatives are going to show up in our lives. We don't need that for this problem. We're just trying to find the units, but I sort of want to shadow how this might come up in context. Okay, so for all the problems we're going to be looking at in the next set of things, we're really thinking about how to apply units to things that either we have already tried to do at some point in one way or to something else that we've been working on. Okay, so let's see. I can make that a little darker. No, I'm not doing a very good job here. Okay, so we want to use what we learned in the last class about approximating a derivative, and we want to bring in this idea of units. So for this problem, we want to approximate g prime of 20. So we're interested in the slope of the tangent line when the independent variable equals 20. And we want to bring in units. So hopefully you can see this. This says kilograms, kg, and this says t, age in weeks. So we have kilograms and we have weeks. And so we are trying to approximate the slope of the tangent line at 20. So here's the point at 20. So again, what we were doing last time, if we have the paper printed out, you can draw a line. Otherwise, you have to sort of visualize the line and try to think of 2 points through which that line crosses. We use those 2 points to approximate the slope of the line. Okay, so I'm going to have you try this. If you don't have this printed out, you can sort of try to visually think about where that tangent line is going to go and see if you can come up with 2 points. And again, find the slope. And once you have approximated the slope, make sure you include your units of what the derivative will be. Okay, so I'm going to give you 2 minutes and then we'll go through it together. So give it a try. right, so finish up whatever part you're working on. Okay, so as usual, your approximation may not be exactly the same as mine, depending on how you drew your line and where your points go, but there should be some similarities. For example, no matter how you draw your tangent line, you should come up with a positive slope. It should be upward sloping from left to right. So when you calculate the slope, it should be positive. And again, once you see sort of the solution I write up, your solution should be in the same general area, right? It might be a little bit bigger, a little bit smaller, depending on your tangent line, but it should be near the answer that I got. So you can see that on my tangent line, when I drew this in, I labeled a couple of points that it looks like it went through. I mentioned before that you can use the point where it touches, or you can use really any 2 points on the line. It doesn't matter which points you use, but they should all be on the line. You want to pick ones that are convenient for you based on the values that they go through. So here, what I did is I used these 2 points. I didn't actually use the point where it touched, but you can. So here, the slope is the change in y over the change in x. So you have 1.5 minus 0 over 40 minus 16. And if you crunch that number, I just put it in my calculator. I got 0.0625. So that's the value, that's the numerical approximation that I got. Yours should be sort of similar. It doesn't have to be exactly the same. Maybe you got 0.08 or 0.04, something like that. But we also still need to talk about the units here because there are units given. So here, again, we're going to do dependent units over independent units. The dependent variable goes on the vertical axis. So that's kilograms. And then the independent units go on the independent axis, which is horizontal. So kilograms per week. I don't know how I forgot an E there. Okay, so I would say half the time there will be units involved in the problems we do, half the time there won't. If there's no units listed there, you don't need to include units in your answer, obviously. But if there are, it's good practice to include them even if that's not the point of the problem. You want to get used to making sure that you can attach them so that when you talk about what answers mean, you have the right context and units involved. Okay, so we're going to do another problem, and this one is a little bit tricky. So the next problem is going to be a statement interpretation, right? So the time for a chemical reaction, capital T in minutes, is a function of the amount of catalyst present, A, in milliliters. So T equals F of A. So first for part A, you're interpreting the statement F of 100 equals 7. So this goes back to what we were doing in chapter 1, right? So what do these numbers mean? What are their units? How do we put it in a sentence? And then part B is F prime of 50 equals 4. So this is where we're really working on our derivative units. So what are the units of 50? What are the units of 4? And how do we put this into a sentence? Just be really careful. I would say start with labeling what is your dependent and what is your independent variable. And then make sure that you attach the independent value with the independent variable and the dependent value with the dependent variable, so on and so forth. Okay, so I'm going to give you 2-ish to 3 minutes to sort of write out a sentence for each of these. Again, the key thing you're looking to do is attach the number to the right units for when you're talking about it. Okay, so try it out. Feel free to check in with someone next to you, and then we'll go through it together. All right, take about 30 more seconds to finish up whatever part you're working on. All right. So part of the reason why this particular problem is a little tricky is that here my dependent units are minutes, right? So it's the capital T. Almost 95% of the time we're working with units. If we have time, it's going to be the independent units. But in this particular instance, it's the dependent units. So we have to keep reminding ourselves of that when we talk about what different things mean, right? Because it's a little weird. It's a little backwards than what we're used to. So our independent units here are milliliters represented by the variable A, okay? So when we have f of 100 equals 7, the number inside the 100 is the independent units. So this 100 is the milliliters, okay? And the 7 here is the dependent units, which are minutes. Okay, and so we need to write a sentence that sort of describes this. And this is where it's tricky again, because time is not given the way we're used to. So we would say something like, when 100 milliliters of catalyst, because remember that 100 milliliters is talking about the amount of a catalyst, which is something you add to a reaction. When 100 milliliters of catalyst are added, the reaction takes 7 minutes. Okay, because the 7 tells us how long this chemical reaction takes. So when we talk about 7 minutes, we are referring to the reaction time. So we want to make sure we have that word reaction. Obviously, this is not the only way we can write this sentence, but the key things are that we're talking about 7 minutes and 100 milliliters, and that each of those has reference to the thing it's talking about. So 100 milliliters of catalyst and 7 minutes is the time of the reaction. So as long as those things are together, you can sort of work this in several different ways for a sentence, but those are the key pieces that need to be together. So again, this first part is just evaluating a function at a point. The second part is looking at the rate of change or the derivative of the function at a point. So now we have to bring in what we know about units of derivatives. So again, the number that's inside the function, this 50 right here, that is also still going to be an independent value, right? So no matter what, you're always plugging in an independent value, whether it's the original function or the first derivative. So here that 50 is again in milliliters. I'm just going to put ml for milliliters. But the 4 here is where we now need to figure out the dependent units over the independent units, right? So the dependent units here were in minutes, and the independent units are in milliliters. So we have 4 minutes per milliliter. So when we're thinking about how to write a sentence that brings in 50 milliliters and 4 minutes per milliliter, we need to think about what this is telling us. So remember, the 50 is telling us at a certain point. So we're going to say something like, when 50 milliliters of catalyst are present, the reaction. So now we're going to be talking about the reaction, which is the second part of this. So this is the rate of change, right? And so because the derivative is positive, we know that the rate means that the original function is increasing. So the reaction is increasing by 4 minutes per milliliter. So what does that mean? So that means if there's 50 milliliters of catalyst and I were to add 1 more milliliter, it would increase my reaction by 4 minutes, right? So it's 4 minutes for every additional milliliter I add. That's what that rate is telling me. So again, the key things I want to group together is that I'm talking about what happens when we have 50 milliliters of catalyst. And then I want to talk about how the reaction is changing in relation to the derivative, which is 4 minutes per milliliter. Again, I'm able to use the word increasing because I know from a previous class that if the derivative is positive, that tells me that the original function, which is talking about the reaction, is increasing. Okay, so again, there's a couple different ways you can word this sentence, but as long as you've grouped together the right key things, that's what we're really getting at here. Okay, so let's look at one more example where we're looking at units. Again, we are trying to make sure we feel comfortable identifying the independent and dependent variables so we can attribute the units correctly here. So there's also sort of a curveball question in part B, just to make sure we can link back and recognize things as they come along. So for this example, it says the amount of medicine in milligrams in the bloodstream, C of T, is a function of time T in minutes after taking the drug. So we want to interpret the statement C of 35 equals 90. So again, we're trying to figure out what are the units of 35, what are the units of 90. Part B says write the derivative of this function using Leibniz notation. So remember what we said about Leibniz, right? We have dependent over independent. So we want to just use the right variables here. And then for part C, interpret the statement C prime of 15 equals 7. So again, what are the units of 15 and what are the units of 7 based on what we know? So again, I recommend you start with identifying what is the independent and dependent variable and what are the units. And then you can start attributing these different numbers to the right units. So I'll give you about 2-3 minutes to see if you can work those out, and then we'll go through it together. All right, take about 30 more seconds. All right, so let's take a look at this. So again, we're just carefully going through, making sure we know what is the dependent and independent variable so we can get the right units to the right place. So here, my dependent variable is C of t, which has the units of milligrams. And then my independent variable is time, which has the units of minutes. So here, for the first statement, we have C of 35 equals 90. So this is straight attachment of units. We're not doing the derivative quite yet. So here we're talking about 35 minutes. Right? Because the number we plug in is the independent value. And then here, the 90 is in milligrams, the dependent variable. So here, if we were going to come up with a sentence, we would say something like, after 35 minutes, there is 90 milligrams of the drug in the bloodstream, something of that sort. So again, 35 minutes is the amount of time since you've ingested it, and then 90 milligrams is the amount of the drug present. For part B, if we're going to write the derivative using Leibniz notation, remember we have the D's. And so we want the variable that represents the dependent variable on the top, so DC. And then on the bottom, we want the independent variable, which is T. So if we were going to talk about the derivative using Leibniz notation, it would be dC dt. So dC dt is the derivative of C with respect to T. Okay. And for part C, when we're interpreting the statement C prime of 15 equals 7, again, the number that gets plugged into the function is your independent value. So here, we're talking about what's happening after 15 minutes. And then the 7 is where we have to now find our derivative units, which are the dependent units over the independent units. So the dependent units are in milligrams, and the independent units are in minutes. So if we're going to put together a sentence, we would say something like, after 15 minutes, the amount of drug in the bloodstream is increasing by 7 milligrams per minute, right? So it's increasing by this amount. And again, I know it's increasing because it's positive. So we're increasing by 7 milligrams every minute, right? And that makes sense because if you take like an Advil, you don't just automatically have all the milligrams there, it releases into your bloodstream. So after 15 minutes, it's still releasing into your bloodstream at this rate, okay? So hopefully through these examples, you're getting comfortable attaching the units to the right numbers. Like I said, this is sort of an add-on to what we do, where we'll now be including units and different things that we talk about in other sections. So we want to make sure we're comfortable setting those things up. Okay, so the next thing we're going to talk about is something called the tangent line approximation, also known as local linearity. So these are the same things, two ways to talk about the same thing. And so what we want to do now is we want to take our knowledge about functional values and derivative values and use that to start making approximations or predictions about values of functions in other places. So what does this mean? So as I mentioned sort of the very first day of class, the powerful part of calculus is being able to predict what we think will happen at another point on a function, right? So what this says is if we have information about a function at a point A and information about the derivative at that same point, we can use it to try to make a good approximation about another value on that function, okay? So what does this mean? So the different parts of this, f of x is the point that we're going to be trying to predict, right? We're going to approximate what the value is. F of a and f prime of a, those are going to be values that are given to us in the setup. That's the information we have. And delta x is how far away we are approximating from the value we have. So if we have information about what's happening at 10, right? Say we know f of 10 and f prime of 10, and we want to use that to guess what's happening at f of 20. then we are 10 units away, so delta x will be 10. If we want to approximate what's happening at f of 100, we would then be 90 units away, and delta x would be 90, right? So we'll look at one together to make sure we can get all these pieces, but the idea is that if I know the value of a function and how much it's changing at that point, I can use that to try to predict where the function is going or where it's been, okay? So let's see how this works. So example 5, suppose that for a particular function, g of 5 equals 10 and g prime of 5 equals 3. Okay, so that's going to line up to what we need here, the function and the derivative. Use this information to approximate g of 7 and g of 1. So notice here that I don't have the actual function. Like I don't know if it's like x squared plus 2 or ln x minus 7, right? The idea is that I only have information about one particular value and how much the function's changing at that point, right? So if I had the function, I could just find g of 7 and g of 1 by plugging in. I wouldn't need to do an approximation, but I don't. So here, this is going to be the best way to approximate with the information I have. Now, again, I can only use this formula if I have the functional value and the derivative value at the same point. So what does this look like? So g of 7, 7's the value I want. I'm going to take the value I know, so g of 5, plus the rate at which the function's changing at that point, g prime of 5. And now I need to figure out my delta x. So my delta x, which I'm going to multiply here, is how far away I am approximating. And the way that I get that is by looking at the difference between the point that I want, which is 7, minus the point that I have information about. So 7 minus 5. So that means that I am approximating 2 units away. So to go from 5 to 7, I'm moving 2 units away, okay? So that's what my formula looks like. But now I want to plug in these values. G of 5 I know is 10. G prime of 5 is 3 times 2. Now, order of operations is really important here. I have to do this multiplication before I add on the 10. The number one reason that students get these types of problems wrong is that they don't follow the order of operations. They do something like 10 plus 3 and then multiply by 2, which you can't do because there's no parentheses here to make that happen. So 3 times 2 is 6. 6 plus 10 is 16. So my approximation value of this function at 7 is 16. Now, if I wanted to do this for g of 1, the other value that I'm interested in, I set it up the same way. So g of 5 plus g prime of 5. Again, I'm using 5 because that's the information I have, times delta x. My delta x in this situation, the number I want is 1, minus the number that I have, which is 5. So 1 minus 5 is -4. So notice that if I try to predict at a point before 5, my delta x will be negative. Whereas if I pick a point after 5, my delta x was positive. So the direction matters, right? So g of 5 is still 10. G prime of 5 is still 3. But now I'm multiplying that 3 by -4 because I'm 4 units away in the other direction. So again, I have to do the multiplication first. So 3 times -4 is -12 plus 10 gives me -2. So g of 1, my approximation is -2. Now, both of these are approximations, right? We are guessing the value based on the information we have. This is sort of our best way of doing it. But g of 7 is a better approximation than g of 1. And the reason why it's a better approximation is because my delta x is smaller. So the closer you are to the value you have, the better your approximation. Right? So g of 6 is a better approximation than G of 7 because 7's further away. The further away you go, the more error there can be. So keep that in mind if you're ever using this to approximate, in a science class or in a business class to make predictions. The closer you are, the better your approximation. Okay, so let's see if we can take a problem and sort of apply this idea to it by figuring out the notation of the problem, what we're trying to ask, and how we might write about it so that we can use this method to predict a population size. So example 6 says, suppose the population of a town was recorded starting in the year 2000. In 2006, the population of the town was 125,000, and the town's population was increasing at a rate of 3,200 people per year. Use this information to approximate the size of the population in 2013. So we have the size of the town, we have the derivative, the rate of change at a certain point. So think about how we might use the mathematical notation we know to write about these things so that we can use this particular formula. Think about what your delta X is going to be and how we might make the prediction for the size of this town in 2013. Okay, so I'm going to give you about 2 minutes to try it out, see what you can figure out, and then we'll go through it together. All right, take about 30 more seconds. All right, so let's talk about this problem. The main thing that we notice here, and the reason we even know to use the tangent line approximation, is that we have information about this population at a particular point in time, and we also have information about the derivative at that same point in time. So what we want to be able to do to use this formula is a way to write the value of this point in time and the derivative. And there's a lot of ways to do this, right? So I used P of 6 is 125,000 and P prime of 6 is 3,200, right? I used P because we're talking about population and that's sort of a convention in math, but there's no reason you would have to use P. You may have also chose to keep the date. So P of 2006 instead of 6, right? So this said it started being measuring in 2000. So I said, okay, well then T equals 6. So it's 6 years later. But you could use P of 2006 and P prime of 2006. You may not have used P at all. You might have said F of 6 and F prime of 6, right? All of these are fine. It doesn't matter the sort of front end notation. What matters is that you have the value at a point and the derivative at that same point. And those values are 125,000 and 3,200. Since we weren't given specific notation to use, you can use whatever notation feels best to you. Okay, like I said, I used P, but if you didn't use P, that's not a problem, right? That's not going to change your final answer here. So what are we actually looking for? We're looking for the population in 2013. So I'm just going to use this notation because that's how I wrote it up. But if you use different notation, that's fine. It might look slightly different. So here, if I'm trying to figure out the population in 2013, I would have P of 13 because I'm using T equals years since 2000. So that means I'm going to have my population in 2006 plus P prime. And then my delta X here is 13 minus 6. So how many years it's been? That's going to be 7. So no matter your notation, your delta X should be 7 years because it's been 7 years since you've gone from 2006 to 2013. Okay. Now, P of 6.
Hey, Dina?
Yes.
Oh, we lost you for about 10 or 15 seconds there.
Okay. So when we set this up, P of 13 is the year we want. So 2013. And then P of 6 and P prime of 6 is the information we have. So this is lining up with our formula here. But your delta X should be 7 no matter what your notation is. So here we have 3,200 times 7. And so your calculation, no matter what your notation is, should be this calculation, 125,000 plus 3,200 times 7. So as long as that's the calculation you get to, then whatever notation you use is totally fine. So again, I want to remind you that the order of operations is really important, which means we have to do the multiplication first. So the 3,200 times 7 is going to give me 22,400. And then I will add that number onto 125,000. So that's going to give me 147,400. So that's my approximation for the population in 2013, right? So what I'm saying here in the background is I started at 125,000 and I'm growing by 3,200 people per year. So since I want to know what's happening in 7 years, I just multiply 7 times 3,200 and add it to the amount I already have, right? So here it's an approximation. How good is it? Well, we're 7 years out. So if we were looking at the population in 2007, that would be a pretty good approximation. In 2013, not quite as good, right? Because now we're 7 years out instead of 1 year out, and the population rates can change year to year. So it's an okay approximation, right? But it's the best we can do with the information we have. Okay, so that's one way that this comes up. Another way that this comes up is in table form, right? So we've spent some time thinking about what tables tell us, what the data means, how to approximate the derivative. So we want to take that and see if we can use this to make a prediction, okay? So suppose the table below gives the total sales in millions of CDs for a music store as a function of time in years. I'm going to go ahead and assume that you all know what CDs are because I'm not willing to admit that I am old. So here, what this tells me is that in 2008, there were 6.25 million CDs sold, which is probably true, right? In 2012, there were 4.25 million CDs sold. We can see that the number of sales is decreasing over time, which makes sense because as streaming music has come along and things like MP3s, people buy less CDs. Okay, that's what we're talking about in this table. We want to use this table to estimate the sales in 2013. So what do we need to do to approximate the sales for a value that's not on the table? We need to do an approximation. So that means we would need to use the value at a point and the derivative at a point. Well, we have the value at 5 different points that we could conceivably use. However, we know that the further away we are from our approximation, the worse it is. So when we pick a value to use, we want to use the closest possible information we have to 2013. And so that will lead us to using the information from 2012. So we need the value at 2012, which we can get from the table, but we also need the derivative in 2012. So in order to get the derivative, we have to use our average rate of change approximation to get the derivative for the approximation for 2013. So there's a lot of moving pieces here that are connecting back to other things we've done. So I'm going to give you about 2 minutes. I want you to try it out, see if you can set up the syntax like, f of 2012 equals this, f prime of 2012 equals this, right? To set up the formula and see what you can figure out in terms of the prediction, and then we will go through it together. Okay, take about 30 more seconds. All right. So again, there's 5 different values on this table, but I'm using 2012 because that is the closest value to 2013. If I were to use 2008, my approximation would not be as good. So I want to use the closest value. So f of 2012, that's the functional value. I get that value right from the table. That's 4.25 million CDs, right? So now I also need the derivative at that point in order to be able to use my formula. The way that we approximate the derivative on a table, again, is by using the average rate of change. Now, normally I would do this to the left and to the right and then average them, but I don't have that option here because I'm at the end of the table. So I'm just going to use the left-hand approximation. So remember, we're going to do 4.25 minus 4.7, so the change in y, over the change in x. So 2012 minus 2011. So on the bottom, that's just 1, right? So this is going to give me negative 0.45. Okay, so remember, in terms of units, that's negative 0.45 million CDs per year. That's how much my sales are decreasing because it's negative. Now, when I use this in my approximation formula, remember, in order to get this, I'm going to use the information I have, the information about the derivative, times delta x. My delta x here is 1 because it's 1 year from 2013 to 2012. So I plug in my values, 4.5 plus negative 0.45 times 1. I would do the multiplication first, but I know that anything times 1 is just itself. And I get 3.8. And this is in millions of CDs, 3.8 million CDs. Okay, so my best approximation here for my sales for the number of CDs in 2013 is 3.8 million CDs. So again, I had to set up the functional value, I had to approximate the derivative, and then I was able to use the local linear approximation or tangent line approximation. Those are the same thing. Okay, so that's how we would approach that on a table. So again, this is helpful in terms of predicting things and thinking about what may be happening at points that we don't have information about. Okay, so we're going to switch gears. Like I said, we're going to start 2.4 today. And so that is the end of 2.3, and that is called interpretations of the derivative. But those are the two pieces that we have from 2.3. So now we're going to shift gears, once I can figure out where to put my papers, into 2.4. And I sort of hinted that we would get to this because 2.4 is going to be talking about the second derivative. So we saw the example earlier where we saw that acceleration was the second derivative of position, right? And so I want to talk a little bit about notation, about why we need the second derivative, and sort of set the stage for what's going to happen here. So when we talk about the rate of change of a function, there's a lot of instances where we can think about where that might be important to us, like, stocks and weather and all sorts of things. The second derivative is a little more tricky because the second derivative is the rate of change of the rate of change, right? So like that sort of adds this layer of like, what are we even talking about? And so acceleration is a really good example. So let's circle back and think about this like in the big context. So if you have a position function, let's assume you're driving a car and your position function is measuring how far away from your house that you are. So let's say you've driven 20 miles. Your position is 20 miles away from your house, okay? The rate of change or the derivative of position is how quickly your position is changing. So maybe you're driving 30 miles per hour, right? So that's a rate of change. That's telling you how quickly your position is changing. When we talk about acceleration, which is the second derivative of position, we are talking about how quickly your rate of change is changing. So that would be like if you went from 30 miles an hour to 70 miles per hour. How quickly did that change, right? That's acceleration because your rate of change is changing. So you can imagine that for a lot of instances, your rate of change will change. A big one that happened recently, or I guess not that recently, right? There was the big oil spill in the ocean. And when that was happening, it started off that people were measuring how quickly the oil was coming out of the bottom of the boat into the ocean to try to figure out how long they had until the whole thing would be emptied into the ocean. That was like the original calculation people were looking at. And that's a first derivative, the rate of change, the rate at which the oil is coming out of the boat, right? But what was happening is that the pressure from the oil was making the hole get bigger and bigger that was in the boat. And so what they realized is that the rate of change wasn't constant. So it wasn't like it was leaking 30 gallons per second the whole time. It was like 30 gallons per second, then 31 gallons per second, then 35 gallons per second, right? So tracking that rate of change and how that changed helped them figure out how long they had to deal with the situation. And so that's a second derivative. So conceptually, there are a lot of things we actually use the second derivative for. Computationally, you can take as many derivatives as you want. You can take a third derivative, a fourth derivative. The functions that we're working with are not problematic in this way, but we will only be looking at first and second derivatives in this class because that's where the applications mostly lie, okay? So notation. The Newtonian notation for a second derivative has two of these little marks, okay? So if there's one, it's the first derivative. If there's two, it's the second derivative. Theoretically, if you were to go into another class, if you were to see something like this, f triple prime, that would be a third derivative. And then after that, we typically start using numbers. So like f4x is a fourth derivative. Like I said, we're not going to do this in this class. But everything we learn can just be applied to do more derivatives if you ever need to. Okay, so the second derivative for Leibniz notation, you end up with something that looks like this. So again, the twos indicate that we're taking the second derivative of the function, right? And so that's what the notation is going to look like when we're talking about the second derivative. Now, I want you to think back for a minute when we were talking about this set of statements that we were linking together in 2.2, okay? So if f of x is increasing on an interval, then the derivative is positive on that interval, right? That's one conclusion that we found. Excuse me. We found that if the original function is decreasing on an interval, then the derivative is negative on that interval. And if the derivative is constant on the interval, yeah.
Oh, sorry. We lost you again for probably 20 or 25 seconds.
Okay. So we're just reviewing the things we learned from 2.2 about the relationship between the original function and the first derivative. And so here, if the original function is increasing, the derivative is positive. If it's decreasing, the derivative is negative. And if it's constant, we said that the derivative is 0. Okay, it is going to be imperative that you understand this relationship between the original and the first derivative really, really well. Okay, because what's going to end up happening is we're going to add on the relationship between the first derivative and the second derivative and the relationship between the original and the second derivative. So there's going to be 3 sets of relationships that we are maintaining. So the better that you understand this to begin with, the better it'll go overall for the other things that we're going to be adding on. Okay, so I think we will not do the graphs today. So we'll stop here. And so on Thursday, we will pick right up, starting with graphs, diving right into second derivative analysis. So again, please make sure you understand these relationships as much as you possibly can before Thursday. Have an excellent rest of your day.